Chapter 11 in our textbook is entitled Liquids and Intermolecular Forces. Intermolecular forces are responsible for holding liquids and solids together. If there were no such forces, all substances would exist in the gas phase. In Chapter 8 of our text, we spoke of covalent and ionic bonding. These are forces that exist within a molecule. So we call those intramolecular forces. Chapter 11 is going to focus not on the forces within a molecule that keep a molecule together, but the forces that exist between molecules. These forces are called intermolecular forces. The attractive forces between molecules are not nearly as strong as covalent bonds. In fact, in many instances, these intermolecular forces are less than 15% the strength of an actual covalent bond. There are many properties that are affected with respect to these intermolecular forces, things like boiling point, melting point, and viscosity, which is a measure of the resistance of a material to flow. By now, we have a basic understanding of the similarities and differences between solids, liquids, and gases. Gases tend to expand to fill their container. They assume both the shape and the volume of their container. They're fairly easily compressible, and they tend to flow readily, as is the case with a fluid. But gas molecules tend to be spread out. And as the kinetic molecular theory suggests, they tend not to interact with one another except during collisions. Well, it is the nature of those interactions that give rise to things like liquids and solids. When molecules interact with one another, they can condense into a more compact phase. Gas molecules that experience a significant interaction can condense into the liquid phase. Liquid molecules that experience even greater interactions can find themselves in the solid phase. We can do this either by changing the temperature or by changing the pressure. A decrease in temperature suggests less kinetic energy for the molecules in question, and an increase in pressure forces the molecules to be closer to one another. So these interactions, these forces that exist are what keep liquids and solids possible. Essentially, the main difference between the three states of matter is the strength of the intermolecular forces, those forces that tie molecules to one another. The stronger the intermolecular force, the greater the attraction between molecules. Here we see the difference between intramolecular forces, also known as chemical bonds, and intermolecular forces. I noted that melting point and boiling point were going to be quantities that reflected the relative strength of attraction. Well, we notice, as the graph indicates, that ionic bonds tend to result in the formation of substances that have high melting points as well as high boiling points. Even in the case of metallic bonding, we see, for example, beryllium, which has a melting point of 1560 Kelvin and a boiling point of over 2000 Kelvin. And in the case of a network covalent solid, such as diamond, where we see carbon bonded to carbon, bonded to carbon, bonded to carbon, over and over and over in a tetrahedral fashion, we see in this vast array of carbon atoms an extremely high melting point of 3800 Kelvin and a boiling point of over 4000 Kelvin. But these are forces that exist within a given substance. If we look at the idea of intermolecular forces, we would see that substances that experience intermolecular forces, specifically covalently bonded substances, tend to experience significantly lower melting points and boiling points. Well, if these transition temperatures are a reflection of the strength of the interaction, then one might go so far as to say that intermolecular forces are far weaker than chemical bonds. It should be noted that of the intermolecular forces listed, we see dispersion forces, dipole-dipole interactions, and hydrogen bonding. Hydrogen bonding seems a bit misleading because hydrogen bonding does not involve an intramolecular force, but is instead an intermolecular force. Hydrogen bonds are not chemical bonds. Now, these three types of intermolecular forces are essentially listed from the weakest to the strongest. Dispersion forces tend to be the weakest of the bunch, while hydrogen bonding represents the strongest type of intermolecular force. Of these three forces, we see that the first two, the dispersion forces and the dipole-dipole forces, are collectively known as van der Waals forces or van der Waals interactions. Now we're going to take a look at describing each type of intermolecular force. First of all, it should be noted that dispersion forces exist within all substances, even substances that we wouldn't expect to have forces exerted. Let's take, for example, the noble gases. Now, we've been told that the noble gases are called noble gases because they tend not to interact with one another. And that being the case, they're found in the gas phase. But even the noble gases can be condensed into the liquid phase. Helium, the lightest of the noble gases, can experience a liquid phase when subjected to temperatures as low as 4 Kelvin. Now, recognizing that 0 Kelvin, absolute zero, is the coldest temperature theoretically possible, it takes a lot in order for gaseous helium to become a liquid. But the presence of the liquid state does suggest that we can force helium to interact with itself. Now, how does this interaction take place? Well, let's imagine that we have two atoms of helium. In the nucleus, we find 2 protons, and outside the nucleus, we find 2 electrons. Well, those electrons aren't static. Those electrons are constantly moving. Let's imagine a scenario where the 2 electrons in an atom of helium find themselves on one side of the atom. Let's say that they find themselves on the left side of an atom. Well, that atom now, from the right side, seems to have an unshielded nucleus. The atom itself seems to be separated into a positive nucleus and a negative side where the electron density is high. Well, if it is brought into close proximity with another helium atom, those electrons could see that unshielded nucleus and experience an attraction, an interaction. Now, this interaction only takes place for an instant. For this reason, we call it an instantaneous dipole, where we see the separation of charge into a positive pole and a negative pole. As soon as the original atom's electrons reorient, then that disrupts the interaction between two atoms. The thing is, this is constantly taking place. The electron cloud around a nucleus is constantly being distorted and affecting the neighboring atoms. The tendency of an electron cloud to be distorted is called its polarizability. Another way of thinking of polarizability is how easily can an electron be fooled by the electron density in a neighboring atom. Well, there are several factors that affect this idea of polarizability in an atom. The number of electrons in an atom is a factor, in that the more electrons you have, the more likely they can be fooled, if you will, or the more likely the electron cloud can be distorted. So if the electron cloud is distorted, that brings forth the possibility of an interaction, even if it's only for an instant. The first polarization results in what we call an instantaneous dipole. The fact that it induces another atom or molecule to interact with it suggests a change that we call an induced dipole. So the constant formation of instantaneous dipoles and induced dipoles are what we call dispersion forces. And because all substances have electrons, all substances can experience dispersion forces. Now, the more electrons, the more dispersion forces. Also, the size of the atom or the molecular weight. Typically, the larger the atom, the more electrons, and the more electrons, the more dispersion forces. Lastly, the shape of the molecule. If a molecule is elongated, has a greater surface area, then two molecules of the same type can find themselves interacting in a more polarizable manner than if the molecules are compact. If you look at the right-hand side of your screen, you will see two compounds, neopentane and pentane. They both share the chemical formula C5H12. But in the case of neopentane, perhaps you can see that as a spherical molecule, the internal electrons aren't experiencing any type of polarizability, or not nearly as much as they would be if they were more exposed. So the more electrons that are available to be distorted, the more dispersion forces. In the case of the spherical neopentane molecule, there are fewer forces because there are fewer electrons exposed for that interaction. Now, this is reflected in the boiling point of pentane versus neopentane, where neopentane has a lower boiling point, which means fewer intermolecular forces. Polar molecules are those molecules in which we see unequal sharing between the atoms with regards to the electrons. And this relates back to the idea of electronegativity. The more electronegative an element, the greater the tendency of that element to pull electron density towards it. If it is higher in electron density, then it would be partially negative. It's pulling electron density away from an atom, which would be partially positive. So if we walk away with a molecule that is partially negative on one end and partially positive on the other, that can give rise to attractive forces between molecules. If that molecule encounters another molecule of the same type, then the oppositely charged ends will attract one another. Negatively charged ends will attract the positively charged ends of neighboring molecules. This is yet another type of intermolecular force that we call dipole-dipole interactions. For molecules of approximately the same size, we see that the dipole-dipole interactions can significantly affect the boiling point, the melting point. These quantities that are a reflection of intermolecular forces. Well, the more polar a molecule is, in other words, the greater the electron density difference, the higher the boiling point. Because with increased polarity, we see greater intermolecular forces. And the more intermolecular forces, the higher the transition temperature, whether it be the boiling point or the melting point. So which of these two forces, both of which are classified as van der Waals interactions, would have the greater effect on things like the boiling point and the melting point? Would it be the dipole-dipole interactions or the dispersion forces? Well, again, the idea of dispersion forces lies in the polarizability of electrons. So if one molecule has a lot more electrons than the other, then perhaps dispersion forces would be the telltale sign when determining those physical properties. But if we have two molecules that are about the same size and about the same shape with about the same number of electrons, the presence of dipole interactions would be the likely determining factor. The image on the right shows the trend between the boiling point and the molecular weight of a series of hydrides. Now, a hydride is a covalently bonded compound that involves hydrogen interacting with another nonmetal. Each of the four lines suggests a different group on the periodic table interacting with hydrogen. The orange line at the bottom shows the group 14 elements, carbon, silicon, germanium, and tin, interacting with hydrogen. In doing so, we see methane and silane and germane and stannane, all in order of increasing molecular weight, also in order of increasing boiling point. And based on the idea of polarizability, that makes sense. The more electrons, the more polarizable the molecule. The more polarizable the molecule, the greater the intermolecular forces. The greater the intermolecular forces, the higher the boiling point. But with the other three lines, we see a bit of a deviation from the norm, particularly at the beginning of the trend. We see ammonia, which has a higher boiling point than pH3. We see HF having a higher boiling point than HCl. We see H2O having a higher boiling point and a significantly higher boiling point than H2S. After this first hiccup, we see the general trend continue for increasing molecular weight, giving rise to an increased boiling point. But what is it about these three molecules? What is it about hydrogen fluoride? What is it about water? What is it about ammonia that causes such a high boiling point? The answer lies in a concept known as hydrogen bonding. Hydrogen bonding is essentially a really powerful dipole-dipole interaction. Specifically, when hydrogen is bonded to a small electronegative element, particularly nitrogen, oxygen, or fluorine, we see an extremely strong dipole-dipole interaction between molecules. These interactions are called hydrogen bonds, and the concept is hydrogen bonding. It should be noted that hydrogen bonds are not covalent bonds. The term hydrogen bond refers to the attraction between the hydrogen on one molecule that is attached to a highly electronegative atom and the small electronegative atom on another molecule. So the hydrogen on a molecule of water being attracted to the oxygen on a neighboring molecule of water. Hydrogen bonding represents the strongest of the three types of intermolecular forces. Now, what is it about hydrogen bonding that makes it such a strong intermolecular force? Well, in part, hydrogen bonding can be attributed to the high electronegativities of nitrogen, oxygen, and fluorine. Hydrogen is such a small atom that nitrogen, oxygen, and fluorine, when bonded to it, can draw electron density extremely towards themselves, leaving the molecule in a very polar fashion. The hydrogen end being slightly positive because the electron density has been drawn away, and the nitrogen, oxygen, or fluorine end being partially negative since the electron density is being drawn towards it. It should be noted that these are the three elements that, in combination with hydrogen, give rise to hydrogen bonding. An interesting example of hydrogen bonding can be seen in the aberrant behavior of water. Typically, when solids melt, they take up more space. When liquids vaporize, they take up more space. And the reverse would hold true. When gases condense into the liquid phase, they take up less space. When liquids become solid, they tend to take up less space. They become more compact. They become more dense. But it turns out that liquid water is more dense than solid water. Liquid water is more dense than gaseous water. It's because of the hydrogen bonding structure in ice. We see an open structure, a rigid structure that optimizes hydrogen bonding. In the image, you can see a series of regularly ordered hexagons, which speak to the high degree of ordering that we see in ice. Upon heating, the regular structure collapses, and we see the resulting liquid water taking up less space than the ice. It's for this reason that we see that ice floats, ice being a less dense state than liquid water. So aquatic life can survive in winter because of this very phenomenon. In areas where we see lakes and rivers and cold weather, we see that the ice that forms will form at the top. So the aquatic life can continue to exist at lower elevations. This same phenomenon shows us that water expands when it freezes. In cold weather, frozen water in pipes may cause them to burst because as the liquid water flows through, upon cooling, the water will take up more space, expanding and perhaps bursting the pipes. So that's just a little example of hydrogen bonding in action. So essentially, to summarize, dispersion forces are found in all substances. The strength of these dispersion forces depends upon the shape of the molecule and the size in terms of their molecular weight. Dipole-dipole forces can add to the effect of dispersion forces, but note that they are only found in polar molecules. Hydrogen bonding is a special case of dipole-dipole interactions. You could call it an extreme form of dipole-dipole. And of these three types, hydrogen bonding is the strongest of these intermolecular forces. So if the molecules of two substances have similar weights and shapes, then their dispersion forces would be similar. The greater the polarity, in other words, if there are dipole-dipole interactions, then the stronger the intermolecular forces. Molecules capable of hydrogen bonding will typically have the strongest interactions. Now we're going to attempt to relate the concept of phase transition to the idea of intermolecular forces. Well, the general idea is the more intermolecular forces that exist, the more likely a substance is to be found in a more compact state of matter. In the case of a solid, we tend to see a great degree of intermolecular forces, which are essentially gluing these molecules together in a rigid array. By increasing the temperature, we're supplying energy to the molecules, which allow them to overcome those interactions. So by adding energy to a solid, perhaps we overcome those interactions that keep something in the solid phase and cause it to transform into the liquid phase. By adding more energy still, we add enough energy to disrupt the interactions to the point where these molecules do not interact with one another except during collisions, henceforth sending this matter into the gas phase. The image that you see is an indicator of the various phase changes. When going from the solid to the liquid, we call that process melting or fusion. The reverse process is freezing. When going from the liquid to the gas, that concept is called vaporization, while the reverse is called condensation. And lastly, when a substance goes directly from the solid phase all the way to the gas phase, it's called sublimation. The reverse process is known as vapor deposition. And there are energy changes associated with each phase change. The heat of fusion is the amount of energy required to convert a solid to a liquid at the melting point. The heat of vaporization is the amount of energy required to convert a liquid to a gas at its boiling point. And the heat of sublimation is the amount of energy required to convert a solid directly to the gas phase. Now, these processes do not happen as simply as you might think. For example, does 0 degrees Celsius represent the melting point of ice or the freezing point of water? It seems like a trick question. What does water at 0 degrees Celsius look like? Before we explore that question in greater detail, let's take a look at the image at the bottom of this slide. For 4 different substances, butane, diethyl ether, water, and mercury, we see the values of heat of fusion, heat of vaporization, and heat of sublimation. In each instance, we see that the heat of fusion is less than the heat of vaporization, and that they are both less than the heat of sublimation. Well, hopefully this makes sense. The amount of energy required to convert a solid to a liquid only involves enough energy to disrupt a particular set of interactions. The molecules are still interacting in the liquid phase. We've just supplied enough energy so that they are no longer in the solid. In the case of the heat of vaporization, we're supplying so much energy that these molecules don't have anything to do with one another. So much energy that any basic interactions are being overcome. And the heat of sublimation is going to be greater than both of them because we have molecules in the solid taking on enough energy to break apart into the gas phase. Now let's get back to the question of water. What exactly does water look like at 0 degrees Celsius? In order to answer that question, we need to look at the behavior of water with respect to a heating curve. A heating curve is a graph of temperature versus the amount of thermal energy added. So let's imagine water at -4 degrees Celsius. At -4 degrees Celsius, water is going to be found in the solid phase. As we increase the temperature to -3 degrees Celsius, water continues to exist in the solid phase. At -2 degrees Celsius, at -1 degree Celsius. At 0 degrees Celsius, we start to see the transition from solid water to liquid water. But fundamentally, we have to think about what temperature actually means. Temperature is a measure of the average kinetic energy of all the particles that make up a sample of matter. So if the average temperature we find at 0, if that represents the average kinetic energy, that means that some molecules are moving faster and some molecules are moving slower. Those that are moving faster are going to go off into the liquid phase. Well, what happens to the average kinetic energy of the molecules that remain in the solid phase? The average goes down. If the fastest of the fast leave and are no longer considered in the sample, then the average of everything that remains goes down ever so slightly. The next bit of energy that is added gets us back up to 0 degrees Celsius so that the fastest of the fast can go off into the liquid phase. The temperature, once again, a reflection of the average kinetic energy of the remaining ice molecules, drops down a little bit. So we add more energy to get back up to 0 degrees Celsius. It is for this reason that the heating curve for water at 0 degrees Celsius does not increase as we put heat in. Instead, if we look at points B and C, that is the point where we are seeing melting taking place. The more heat that we add, we see the conversion of all of the solid water being converted to liquid water. It's only when all of the water has been melted that we see an increase in temperature as a result of heating. So as we increase the temperature from 0 degrees Celsius all the way up to 100 degrees Celsius, we're about to see a similar phenomenon take place. At 100 degrees Celsius, liquid water is preparing to go off into the gas phase. 100 degrees Celsius represents the average kinetic energy of all of the molecules in a sample of liquid water. The fastest of the fast go off into the gas phase. What happens to the average kinetic energy of everything that remains in the liquid phase? It drops down just a little. The next bit of heat that is placed in gets us back up to 100 degrees Celsius so that all of the water can undergo vaporization. Each of these red lines represents the heat of transition, whether it be the heat of fusion with respect to melting or the heat of vaporization with respect to vaporizing. A change in temperature is but one of the ways in which we can see phase transitions take place. A gas can condense into the liquid phase through the lowering of temperature, but it can also be liquefied by adding pressure, by forcing the molecules to interact with one another. The temperature beyond which a gas cannot be compressed and form a liquid phase is known as the critical temperature. Another way of saying that is the critical temperature is the highest temperature at which a substance can exist as a liquid. The process of liquefying a gas by adding pressure is known as liquefaction. And the pressure required to compress a liquid at its critical temperature is called the critical pressure. We typically think of the boiling point of water as being 100 degrees Celsius. So at 105 degrees Celsius, we tend to think of water being in the gas phase. But if you take water at 105 degrees Celsius and increase the pressure, you can force it back into the liquid phase. If we take water at 120 degrees Celsius, by applying pressure, we can force it back into the liquid phase. Now the pressure is going to be higher than 1 atmosphere worth of pressure. By increasing the pressure, we find ourselves forcing those gas molecules back into a liquid phase that we wouldn't see under normal atmospheric conditions. In a moment, we're going to speak to an instance where we monitor the behavior of a substance beyond the critical temperature and beyond its critical pressure. The state of this substance will be known as a supercritical fluid. The table here shows a series of substances and their critical temperatures as well as their critical pressures. Let's look at water, for example. At the bottom of this table, we see water having a critical temperature of 648 Kelvin. That corresponds to a temperature of 375 degrees Celsius. So at 375 degrees Celsius, water can exist in the liquid phase. It just requires an insane amount of pressure, specifically 218 atmospheres worth of pressure. Water at any higher temperature cannot exist in the liquid phase, no matter how much we compress water at 392 degrees Celsius. We cannot condense it back into the liquid phase. Above the critical temperature, it is impossible to convert a gas into a liquid simply by adding pressure. If you take note of the critical temperature of carbon dioxide, 304 Kelvin. Now that's not a very high temperature. 304 Kelvin is just 31 degrees Celsius. Yet and still we tend to think of carbon dioxide as a gas. Well, let's take a look at the critical pressure of carbon dioxide, 73 atmospheres worth of pressure. In a moment, we're going to be able to envision a pressure versus temperature curve in which we look at the relationship of liquid carbon dioxide, solid carbon dioxide, which we call dry ice, and gaseous carbon dioxide, and what it takes in order to convert between those three states. Here's a bit of a hint. I don't know if any of you have laid eyes on liquid carbon dioxide. The process of vaporization is typically a surface-based phenomenon. Liquid molecules at the surface have enough energy to break free from the liquid phase and go off into the gas phase. If we have a closed container, then those molecules, as they exert pressure, can in turn interact with the liquid phase and recondense, forming a liquid. As more and more molecules escape the liquid phase, the pressure that they exert in the gas phase tends to increase. As the image at the bottom suggests, we see liquid molecules going off into the gas phase. And the more and more gas phase molecules we make, the more likely we are to see them condensing back into the gas phase, or rather into the liquid phase. At some point, we're going to reach a situation where the rate at which liquid molecules vaporize and vapor molecules condense is the same. At this point, we define it as dynamic equilibrium. The vapor pressure of a substance is defined as the pressure that a vapor will exert when in dynamic equilibrium with its liquid. So when dynamic equilibrium has been reached, the pressure exerted by gas phase molecules is known as the vapor pressure. The boiling point of a liquid is the temperature at which the vapor pressure is equal to atmospheric pressure. The normal boiling point is the temperature at which that vapor pressure is equal to 1 atmosphere of pressure, or 760 torr. So at sea level, where the atmospheric pressure is 1 atmosphere, we refer to the normal boiling point of substances. If you look at the blue curve that represents water, we will notice that with the pressure versus temperature curve, or what we call a vapor pressure curve, we see that with increasing temperature, we see an increase in the vapor pressure of a substance. At 100 degrees Celsius, we see the normal boiling point of water. We typically think that water boils at 100 degrees Celsius, but that's only at 1 atmosphere of pressure. We find that at higher temperatures, the vapor pressure of water is even higher. At lower temperatures, the vapor pressure of water is lower. So if the atmospheric conditions are such that we are at 695 torr, which is slightly less than 1 atmosphere of pressure, then water would boil at a temperature slightly less than 100 degrees Celsius. It's for this reason that if you look at a package of food, which speaks to the boiling instructions, perhaps you're cooking a rice dish, and it says to boil the water under a certain set of conditions. At higher pressures and at lower pressures, which oftentimes is related to the elevation, we find different cooking instructions. At higher pressures, then you're going to require a higher temperature to boil. At lower pressures, water will boil at lower temperatures. A phase diagram is a plot of pressure versus temperature that shows the equilibrium that exists between all 3 phases of matter. It can also indicate the state at which a sample of matter exists at a given temperature and pressure. Featured in a phase diagram, we see things like the vapor pressure curve, sublimation curve, and various phase transition data with respect to pressure and temperature. By observing the image at the bottom of the slide, we can see that at low pressure and low temperature, substances tend to exist in either the solid phase or the gas phase. At low pressures, matter that exists in the solid phase, upon heating, can be converted directly to the gas phase via sublimation. At higher pressures, solids tend to go through the liquid phase and then through to the gas phase. A sample of matter that goes through all three states might be water. Let's think about water. At really, really low temperatures, water exists in the solid phase. As we increase the temperature under normal atmospheric conditions, water goes from the solid through to the liquid phase. By continuing to add energy, it goes through to the gas phase. But for a substance like carbon dioxide, the liquid phase lies significantly higher on the vapor pressure curve and on the phase diagram than we would see under normal atmospheric conditions. The pressure, that is atmospheric pressure for carbon dioxide, would fall below the vapor pressure curve indicated by the red line. So under normal atmospheric conditions, solid carbon dioxide, otherwise known as dry ice, undergoes sublimation. We would have to increase the pressure of gaseous carbon dioxide in order to go from gaseous carbon dioxide to liquid carbon dioxide. And that, ladies and gentlemen, is a summation of chapter 11. Oh wait, I'm sorry, one last thing. A phase diagram also indicates two specific points. One point is called the triple point, indicated by the T on your image, and one called the critical point, indicated by the letter C. The triple point of a substance is the temperature and pressure at which all three states of matter can exist in dynamic equilibrium. So for a given temperature and pressure, the matter will exist in the solid phase, the liquid phase, and the gas phase simultaneously in the same amounts. The critical point is defined by the critical pressure and the critical temperature. So remembering that the critical temperature is the highest temperature at which a substance can exist in the liquid phase. At higher temperatures, we find substances in either the gas phase or in the form of a supercritical fluid. At the critical point, if we increase the temperature, we see matter in the gas phase. But if we increase the pressure, we instead see matter in a phase that's beyond the critical point, which is neither truly liquid-like or gaseous, but is instead known as a supercritical fluid. Okay, that's all I want to say about chapter 11. I mean it this time.